Excel-based tool for spacecraft thermal design, to be presented by Kevin Anderson of California State Polytechnic University at Pomona.
Dr. Anderson, who was slated to give the presentation, could not be here, so I, Ariel Gotti, a co-author, will be giving the presentation. Quickly talk about, this is the outline, and I'll quickly go through because I know that we're crunched for time, about the Excel-based thermal tool. So this paper really will talk about the ability to use Excel as a thermal analysis tool. Now, the ETA, Excel Thermal Analyzer, is self-contained within Excel. It's written in Visual Basic as a macro. ETA really takes advantage of mature spacecraft designs, although you could also actually build something from scratch if you wanted to. But it quickly gives you an answer to your thermal network in a matter of minutes, typically. So this paper will present the methodology used. This particular tool has been validated. It was written, I dare say, about 20 years ago, and it's been used extensively in those 2 decades. The nice thing about this particular tool is that you can easily do a 1, 2, 3 noder problem, or you can basically do a problem that has thousands of nodes and tens of thousands of conductors. The only limit that it has is the number of rows in Excel. And last time I checked, you can get like 1.2 million rows. So you can have that many nodes and conductors. So that's the beauty of it. Thermal Excel is not meant to compete with Thermal Desktop or ESA-TAN or any of the major providers. That is not his task. His task is to give the thermal engineer the ability to do quick and dirty calculations. This is the thermal interface, and it really it's very simple. You provide a node range, a conductor range, and a heat, and you're able to do steady state, and it gives the thermal engineer the ability to do things that thermal engineers usually need to do. You can look at a heat map, QMAP. You can prune certain conductors by providing a new factor. So if you want to kill a conductor, you can kill it. So you can do many things that thermal engineers can do. And you can do that all within Excel. So the methodology is based on a fundamental paper that was written by Ishimoto and Fink in 1971. And they were with TRW, which is now Northrop Grumman, but it was sponsored by NASA. So the methodology has been around for quite a while, and it just basically follows a steady state heat balance equation for all the nodes, and it's very simplistic. The equation is given there, and the ETA tool basically iterates in a steady state both to a temperature criteria and a heat balance criteria. So, we don't want to violate the first law of thermodynamics. So it does the very basic things that any tool will do, whether you're using a high-end tool like Thermal Desktop or Isatan, or as we just saw earlier, Maya heat transfer technologies. Those are the high-end tools. This little tool provides the same level of accuracy as the higher end tools. However, it's not able to do the things so that those higher end tools can do. There we go. At the heart of the tool, um, we use the pseudo compute sequence, or in the case of ETA, the long pseudo compute sequence, or LPCS. Uh, Cinda, for example, uses the same methodology, and it just identifies the position value of all off-diagonal elements, and basically it optimizes the matrix. So the same methodology that is used in at least in Cinda with an S, and actually Cinda with a C for those old guys out there. It's the same methodology. I'm not exactly sure what Isatan or Maya will use, but Cinda will use LPCS, and that's the heart of the analyzer, both for Cinda and for ETA. Diffusion nodes, and very much like arithmetic nodes, um, it's the same. This is the equation that we're solving. So basically, um, the set of differential equations are solved numerically, and they basically result in this equation. So having a temperature, we will calculate the temperature for the next iteration, and so forth, until the temperatures, the change in temperatures meets a certain error criteria. And then we also check for the energy balance. So stability in temperature and stability in heat. And a similar thing is done for arithmetic nodes. Now, the issue with arithmetic nodes is the fact that they have no mass. So it makes it interesting to do a transient solution. But there is a solution. So they're treated in a similar fashion as they are diffuse. This is a rough flow chart of the steady state solver. But the interesting, aspect of it, and I'll just go really quick, is there is a rhyme and reason to the way that the solver is laid out. So basically, like in any Cinda block, you can have diffuse nodes, arithmetic nodes, and definitely a boundary node. And they are defined in a manner that most thermal engineers are used to. You have a node number, initial temperature, and a capacitance. So that's your node block. Then you move into the conductor sequence, and we can do linear and radiation in any form or variation of them. It can be an all linear network, could be an all radiation network, or it could be any combination thereof. And the way that it's defined is the way the thermal engineers are mostly used to. So conductor number, and if it's negative, it's a radiation. If it's positive, it's a linear. Node 1, node 2, and the conductance between node 1 and node 2. So basically the node and conductor blocks are very similar to what thermal engineers are used to when they do their analysis. And for heating, it's very straightforward. It's the node and the heat that's in that node. And then we just let it rip. The iterations are carried until the criteria is met. So the ETA tool was validated by Dr. Anderson a while back, and he used as a study an actual spacecraft design, high usability host or HUH spacecraft. And this is a graphical model of the spacecraft. And those are the components shown in the graphic of the spacecraft. Simplistic, but this particular spacecraft then was nodalized so that we could calculate temperatures. So the spacecraft had to have a payload accommodation. So all the science components, and they had their operating, temperature limits. We can take that into account within Excel. And it was proposed, the work was to design a thermal subsystem for flight using a combination of bus and payload. So the actual spacecraft had an ACS, or attitude control subsystem, power, data handling, telecommunications. So all those components that usually are part of a typical spacecraft system could be included here. And roughly the dimensions are given of what the system was like. So let's get down to the nuts and bolts. So basically, node and conductors, and you can see the simplistic thermal network. Now, this is simplistic. I've actually have worked with much bigger spacecraft systems that were thousands of nodes with tens of thousands of conductors, much more detailed, that were used for analysis and production of spacecraft. But this is a very simplistic validation that was done by Dr. Kevin Anderson. So as you can see, the linear conductors are defined in Excel in this manner: conductor number, node to node, and the actual conductor. Negative, it tells me that it's a radiation. And for linear, I can see them here under radiation conductors. Although the chart here has them flipped, so I apologize for that. The linear conductors are flagged as radiation conductors and vice versa. So very simple, straightforward to define a network. And you can do that within Excel by putting a value in a cell. Okay. Now, one of the shortcomings, to be sure, in this particular implementation of a thermal analyzer is that it does not calculate environmental loading, does not calculate radiative couplings. It's not meant to. It's not meant to. You already have tools that do that for you. This tool is meant as a back of the envelope calculations. And sometimes those back of the envelope calculations can be pretty involved. And this gives you the ability to solve them. So for environmental loads, they had to be calculated by other means. So the table that's shown here takes into consideration the loads, which were calculated independently, plus the dissipation from the payload and the components within the payload. So the list shows the combined heating, and a cold case and a hot case were done. Okay, so these are the resultant temperatures. So for the cold case and the hot case. So this was something that was verified by Dr. Anderson. So self-explanatory, really. It's just a validation case. Um, so the ETA tool really has proven to be really useful as a thermal analyzer. Like I said, I've used it from small problems, 2, 3, 4 noders, really quickly put them together to validate something from a bigger model, or just to, when a thermal engineer gives me a number, I can quickly validate that the number I was given, makes sense. Um, and I can use it to actually design things. I've actually used ETA to design, test fixtures, test concepts, or flight concepts, or what have you. Also, um, uh, the one of the basic requirements to have a versatile thermal analyzer is that it should be able to handle conduction, convection, and radiation all at once. And this tool can do that. And this tool has been verified independently, not only by myself and Dr. Anderson, but by others, using sample problems and so forth. And this is pretty much the references. So, in conclusion, the tool is meant to be a wrench, if you will, in the thermal engineer's toolbox. I know that the thermal engineer has access to much more sophisticated tools. This is just something they can have in his machine at a fingertip, day and night, to do quick and dirty analysis, or even a little bit more complicated, but basically something that's easy and quick to do. So if you have any questions, I'll be more than happy to entertain.
I have one of my own. This is a tool that I could see being very useful throughout the development cycle for a lot of hypothetical short studies, and especially useful at the start when you're really thinking conceptual design. Do you have kind of some insight into where you see in a development cycle switching from this to a more complex tool like Thermal Desktop or an alternative?
Yes, yes. As a matter of fact, I've used this tool on several occasions where you're trying to develop a concept for a spacecraft of any type, and you have various disciplines. You have the power guys, you have the RF guys, and they all have requirements. So I've been in situations where we lock ourselves into a room and we basically link up our Excels. So the power guy will calculate his requirements then bleeding to my thermal requirements. So I can run my tool, calculate temperatures. I can interface with the RF guy and calculate temperatures. And so basically, all the engineering team can be, if you will, of one mind, and the tool allows you to see if you're going to meet requirements. And once on a notional level, conceptual level, you have something that seems to work, then you're able to take what you generated in this tool and import it directly to, say, Thermal Desktop. So you can now go to town. Now you can put the finishing touches and the details. So I've used this tool to get me 90% of the way to the final design, and then I use the bigger end tools to take me to the finish line.
We're hitting the end of our time block, but we had two requests in chat. One to see the last slide again, if you can show that for a moment, and also a question of where we can find the ETA tool if we want to try using it.
Yeah, sure. Let me share the last slide. This one or the one previous to that one?
I think the references slide.
The references slide. Okay. Anything in particular?
Yes, I think that does it. And
Okay.
to get a copy of the ETA tool, what do we need to do for that?
Yeah. Either, well, I would say email Dr. Anderson, and because it is, something that was done as a uh, love of the industry, um, I'd be more than happy to send it to you, and it's free. I mean, I'm not charging anything for it. So it is a gift to the profession, from thermal engineer to thermal engineer. So it's a macro that interfaces with your Excel, and just send Dr. Anderson an email. He'll let me know, and I'll just forward you the macro, and I can help you install it if you have problems.